This presentation is delivered by the Stanford Center for Professional Development.
I wonder how long I can keep this up. All right. All right, so the first thing any questions, any comments? All right, the first thing I want to do is fix a little mistake I made at the end of last time. I was upset about it for days afterwards, so I just want to correct that. This was in the proof of the central limit theorem, which I hope you will agree was a real treat. I mean, it's just an amazing fact, and the way that it followed, the way that it brings in convolution, the Fourier transform of the Gaussian, and so on, is really, I think, a real highlight of the course. I mean, to see those things emerge, and to the whole spooky nature of repeated convolutions approaching a Gaussian, I think, is just an amazing thing. But I did screw it up at the end, and so I just wanted to correct that. Everything was fine except one final formula that I wrote. So I'm not going to redo it. I just want to point out where I just wrote the wrong thing. It's correct in the notes. I just wrote the wrong thing on the board. This was the setup. So x1 through xn are, as they say in the biz, independent and identically distributed random variables. You don't have to write this down. I'm just recalling what the notation was. And P of little x is the distribution that goes along with all of them, all right? Because they have the same distribution. There's a single function P of x which describes how each one of them is distributed. So it's a distribution for each. All right? And then I formed P sub n of x was the distribution for the sum scaled by square root of n. So it's the average scaled, excuse me, there was some assumption we made on the x's, a normalization that is. We assumed they had mean 0, and we assumed they had standard deviation or variance 1. And then if you form the sum, the mean of the sum is 0, but the standard deviation or the standard deviation of the sum is the square root of n. So it scales by square root of n. So you divide by square root of n to have this sum, Sn I called it, have mean 0 and standard deviation 1. And P sub n of x was the distribution for this. And then what we found was that the Fourier transform, here we go. Here's my formula. The Fourier transform of P sub n at S was the Fourier transform of P at S over the square root of n to the nth power. And then the trick, or the analysis, the way the proof worked was to compute the Fourier transform of P at S over the square root of n, just using the definition of the Fourier transform that used this very sneaky thing of looking at the Taylor series expansion for the complex exponential and integrating the terms and so on. And it was really quite clever, really quite a clever trick. And what I found was that the Fourier transform of P at S over the square root of n was approximately, if n is large, was 1 minus 2 pi squared S squared over n. That was fine. All right, that was fine. And then for some reason, then I raised this to the nth power. So the Fourier transform of P at S over the square root of n to the n was then approximately this thing raised to the nth, 1 minus 2 pi squared S squared over n to the n. And then inexplicably, I had the wrong approximation for this in terms of an exponential, in terms of power of e. That is, this 1 minus 2 pi squared S squared over n is approximately e to the minus 2 pi squared S squared. All right, and I'm going to look that up again to make sure I have it right this time. Sure enough, yeah, okay. All right, so then from there, and for some reason I wrote 2 pi squared over S squared last time, but it's 2 pi squared times S squared. That's an elementary, to the n. That's an elementary fact from calculus that you learned probably a long time ago when you were first learning about properties of the exponential function. Okay, and then from there you take the inverse Fourier transform and you get the result. Ft of this inverse Fourier transform of this Gaussian, e to the minus 2 pi squared S squared to get the result, which I am afraid to write down because I'm afraid I'm just going to make one more mistake, so I'm not going to do it, to get the final result, the central limit theorem. All right. There, I feel better now that I've corrected it. I'm not sure everybody else here feels better, but I feel better. Okay, now, to get on to the day's events. Brothers and sisters, today we have to come to a reckoning with our failings. Today we have to confront some things we have not confronted, but must. Now, first, the good news, and there is always good news. The good news is the formulas we have derived, the applications we have done, are all correct. So relax. Nothing that we have done, strictly speaking, is wrong. However, much has been left unsaid. And today, we have to say it. We have to confront the convergence of integrals. It is a sin to consider integrals that do not converge. And I'm afraid there are times when we have sinned. But in the end, nothing that we have done is wrong. So relax. But much has been left unsaid. So it is time now. Are you ready? Are you ready? Okay, now, so we need to have a better, more robust definition of the Fourier transform in order to I think I got to stop this. There's only so much of this I can do. We need a more robust understanding of the Fourier transform. We need a more robust definition of the Fourier transform that will allow us, verily, to work with the signals that society needs to function. Sines, cosines, even the function 1, constant functions. And the Fourier transform, as we have defined it, will not do the trick. More robust definition. And that's really what it amounts to, definition of the Fourier transform. To deal with common signals. All right, ones for which the classical definition does not work or will not, is not adequate. And the issue is exactly the convergence of the integral. Or, if not the convergence of the integral for the function, applying Fourier inversion. One for which the classical definition, let me just say, will not do. All right? All right, there are two issues, really. All right, one is the definition of the Fourier transform itself. All right, the convergence of the integral defining the Fourier transform. When I say convergence of the integral, I mean just some way of evaluating, some way of making the integral make sense. Convergence of the integral defining the Fourier transform. And the second, and just as important, certainly for applications, it doesn't do you any good to take the Fourier transform if you can't undo what you've done. That is to say, you want Fourier inversion to work also. You want Fourier inversion to apply, all right? Now, it shouldn't be surprised that if there's a problem with the Fourier transform, there's probably, with the definition of the Fourier transform, there may be a problem also with Fourier inversion because the formulas are very similar. One involves the integral of e to the minus 2 pi isx, the other involves the integral of e to the plus 2 pi isx, but really, the issues of convergence as far as that goes are pretty much the same, all right? Now, there are two ways to approach this problem, and so this is a genuine problem, and it really has to be dealt with. And it has been dealt with in various ways over various periods of time. Fourier analysis is a highly developed subject. All right, and it has gone through various stages of development. There are two ways of doing this. In the early stages, I'd say that's probably a fair way of characterizing it, It was done on sort of an ad hoc basis. That is, special techniques were developed for special problems that would explain away a special function or a special signal. All right, so that's one way. Two ways. Two ways of dealing with this, with these problems. And one is, so to speak, ad hoc, special techniques. Special techniques. Got a particular problematic integral? Okay, let me just work with that integral. Right? Having trouble with convergence of a particular signal, having trouble applying Fourier inversion in a particular case, okay, let me deal with that. By some trick, by some method that applies, not generally, but to that one problem that you're having difficulty with, and then you can advance. All right? Till the next problem comes up. All right, and this was okay. This was all that could be done because it was all the understanding at the time it led to. The second approach, and that's the approach that we're going to take actually, is to rework the foundations. All right, that's the second approach. You have to rework the foundations to give really a different definition of the Fourier transform, one that applies more robustly, more equally somehow to all signals that come up all at once. You have to rework the foundations. And the definition. All right. Now, this came much later. All right. This came probably in the 40s, 1940s, say. And by that time, as I say, Fourier analysis was a highly developed, both in its theory and its applications, was a highly developed subject. All right. Now, this gets into mathematically deep waters. All right, which we will not completely tread. But I do want to give you the confidence enough to swim in them a little bit, all right, just so you know what the issues are and know how they were dealt with, all right. And furthermore, the other thing that I want you to get out of this is a certain confidence that you can compute, all right. The method wouldn't be any good, really. It wouldn't be of interest outside of math departments and mathematical circles if it didn't offer a way of computing with confidence when that couldn't be done so much before. All right, you can actually use this method to find specific Fourier transforms in a way that's airtight, that works, and is actually quite nice. All right, and so we'll do that. You should so don't fret over mathematical details. What I'm going to do, what I hope to do, is to sort of take you to the brink of the abyss and then back off. All right, say what the issues are, say where the problems are. But don't deal with the mathematical proofs, and don't deal with all the fundamentals that have to be analyzed, because it's quite daunting. All right, there's a huge amount that has to be done, but we don't need that. But I think what you can see is the general structure, the general overall direction to the argument. Now, let me give you an example to show where the issues are. Matter of fact, let's go back to the very first example that we considered, which already shows the problem. And I may have mentioned this before, actually, but now I want to say it a little bit more sternly somehow. All right, so the problem is evident in the very first example. All right, the very first example we had was the rectangle function and its Fourier transform. So f of t is the rectangle function, pi of t. Now, there is no problem at all taking the Fourier transform of that. That's not the issue. Okay, the integral converges. It's a very simple function. So the Fourier transform, as classically defined, is fine. All right, the Fourier transform of the rectangle function is the sinc function. Sinc of s is sine of pi s divided by pi s. All right, that's fine. The problem is inversion. All right, the problem is getting the other way around. Now, we did this by duality. All right. Well, there are really two things. There's either Fourier inversion or finding the Fourier transform of the sinc function. All right. The problem is concluding that the inverse Fourier transform of the sinc function is the rectangle function. We use duality, or more or less equivalently via what we call duality, and that was all fine. All right. Nothing that we did was wrong. It wasn't justified. All right. Via duality, what is the same thing? The Fourier transform of the sinc function is the rectangle function. Okay, same kind of issue. Same issue is involved here in showing this as in showing this. And the problem is writing down that integral. All right. The Fourier transform of the sinc function, or the inverse Fourier transform of the sinc function. Let me just stick with the problem of Fourier inversion. The inverse Fourier transform of the sinc function is the integral from minus infinity to infinity of e to the minus 2 pi I s t. So let me write out the sinc in terms of sine and cosine. Sine of pi s divided by pi s, and I'm integrating with respect to s, so what results is supposed to be a function of t. As a matter of fact, what results is supposed to be the rectangle function. Now, I said at the time, you want to try to evaluate that integral? Good luck. All right, because it's not so easy to do. So again, according to what we expect to be true, this integral turns out to be 1 when s is less than a half, and it turns out to be 0 when s is greater than or equal to a half. It turns out to be the Rect function. Now, even this is actually not quite correct because well, one thing at a time here. In fact, by ad hoc techniques, special techniques, and there are actually a variety of techniques can be brought to bear on this, some more complicated than others, you can actually evaluate this integral. But it's not obvious, all right? No simple integration by parts, no simple integration by substitution is going to get you this sort of result. Okay? This is okay. This result is okay, almost okay. I'll say comment in just a second. Okay, but requires special techniques. And in fact, there's a problem at the endpoints. There's a problem at plus and minus 1 with that integral. You actually have it's equal to 1/2, I think, when s is equal to plus or minus 1/2. So that's another reason for sort of defining the rectangle function that way. So it doesn't jump just rough from 0 to 1, but has a value 1/2 at the discontinuities. Never mind that. Special technique. So it's in fact special problem at the endpoints. At endpoints, s equals plus or minus 1/2. Okay. But anyway, the point is that it can be dealt with. But it's a little bit disconcerting that the simplest example in the entire subject already poses this problem. All right? The most basic function already requires you to do special arguments just so you know that Fourier inversion works. That's a little bit irritating, more than a little bit irritating. Okay? Oh, Jesus. Picky. All right. Yes. There. Good. Don't do that again. Same thing because it's an even function. All right. But anyway. So there. All right. Now, let me take a second example. So there's a problem where it's fine to compute the Fourier transform, but the problem is with Fourier inversion, all right? Computing the Fourier transform of the rectangle function gives you the sinc function, that's fine, but Fourier inversion does not apply directly without some extra work. Now, as a second example of troubles, there are very simple functions for which you can't even get started. And I believe I may have mentioned these before, but let me say them again now in this context of repentance and trying to lead a more virtuous life. So, a second example, consider, well, I can take f of t equals 1, the constant function, all right? Then there is no way to make sense of, in the classical way, of the integral from minus infinity of its Fourier transform. The integral from minus infinity e to the minus 2 pi I s t times 1 dt. There's no way in which this integral can be made to make sense. Period. All right, it just won't work. Now, I know you know, that you write down this integral and you write, oh, that's just the delta function, right? But that comes later. And that comes later really only as a convention, because to write down this integral is to sin in the sense of expecting this to do anything. This integral does not make sense. Can't be made to make sense. And slightly more generally, but equally importantly, other signals do not have classical Fourier transforms in the sense that the integral defines something. The integral is well defined. For instance, sine and cosine have the same sort of problem. Likewise, for, say, f of t equals the sine of 2 pi t, or g of t equals the cosine of 2 pi t, there's no way to make sense. You can't make sense of of the integral from minus infinity to infinity of the classical Fourier transform, e to the minus 2 pi I s t, say, sine of 2 pi t dt. All right? The integral oscillates. The thing doesn't die out as you're tending to infinity. Nothing good is going to happen here. No secret combination of cancellations. No conspiracy of pluses and minuses is going to make this thing work. All right? It just won't work. All right? And these are the signals that society needs. All right? So what is to be done? What is to be done? Now, you remember that the situation is somewhat analogous philosophically, spiritually, heavenly. The situation is somewhat similar to what we confronted with Fourier series. That is, Fourier series was supposed to be a method that applied in great generality. You wanted to be able to write down a very general function in terms of a periodic function, in terms of its Fourier series, right? And then compute with it. But the problem was those series didn't converge in any sense. You couldn't make those series converge. Or maybe you had to make a very special argument to show that it converged and so on. All right? What was finally, and then finally the subject not so much collapsed of its own weight, but a fundamental reworking had to be done. In order to make Fourier series apply as generally as you would like it to apply, you had to really change the notion of convergence. You had to rework the foundations. All right? So it's analogous. So I don't want to make the analogy too sharp or too precise, but it is. But in some sense, it is analogous to Fourier series. We needed reworking of the foundations. We needed a new definition, new conception of convergence. All right, and there's a lot that went on with that. But you had to sort of abandon, if you wanted to advance the subject, and if you wanted to talk about things in greatest generality, you couldn't talk about point-wise convergence. You had to talk about convergence in the mean, and so on. You had to talk about the square integrable functions and all the rest of that jazz. Quite far removed from the initial development of the subject, but it's what had to be done, and ultimately it led to a very fine theory and a very robust and applicable theory. All right. Now, we're going to have to do a similar thing here. But again, Fourier series, Fourier analysis, Fourier series, and then the work on the Fourier transform is a very highly developed subject. So you ask yourself, if I'm forced somehow, because the thing is collapsing, it's too many ad hoc arguments, too many sort of one-off examples that have to be explained. So I really have to rework the foundations. But it's such a highly developed subject that you are confronting the problem that any scientist or engineer or mathematician confronts in a situation like that, is that nature provides you with so many phenomena that have been so thoroughly studied. How do you choose the right ones upon which to base your theory? How do you choose a relatively small number of phenomena upon which, or based on which, the others can be explained? All right? So much had been done in Fourier analysis and applications of Fourier analysis and everything. Where do you start? What do you do? So how to choose the phenomena, how to choose the basic phenomena upon which the others can be, basic phenomena which explains the others, which can be used to explain others. All others. All right, that's the problem. And it's a problem that confronts anybody doing experiment. Think of this as viewing a series of experiments. You know, you do a series of experiments. What are you measuring? And what are you measuring? Is that significant? Is not significant? What do I pay attention to? What do I ignore? I mean, the results are there in front of me. What do I do? Which ones do I choose? All right. So I want to explain how this was resolved. And it was resolved really quite brilliantly and quite decisively in the 40s. The first step, and I'll say a little bit more about the history of this as we go along. The first step in understanding this is to somehow back away from the troubles and concentrate on what works well. All right, that's the first step. So back away from the problems. What is the best situation? Identify the best situation, or what characterizes the best situation. Now, in this case, what that means is you want to identify a class of signals for which everything you want is true. All right? So you want to identify, when I say what is the best situation, I mean identify the best signals, the best class of functions for Fourier analysis. So Fourier, let me just say Fourier transforms. All right? Now, the requirements are these. What we want is we want really just two properties. We want one. Let's call this class of signals S. So think of S standing for signals, but actually S is going to stand for Schwartz, the person who isolated these particular class of functions as the best ones upon which to build a theory. So then we want two things. One, if f of t is in S, then the Fourier transform of t is defined, and it's also in S. The Fourier transform of f is defined classically by the integral. And the Fourier transform of f is also of the same class. All right? Now, that already is rules out, for example, that already tells us, although I haven't defined S yet, you can imagine that it tells us that the rectangle function shouldn't be in that class, and the sine and the cosine shouldn't be in that class, or the constant 1 shouldn't be in that class, because for the rectangle function, there's obviously a problem. The Fourier transform of the rectangle function is a sinc function. The sinc function is not as good as the rectangle function in some sense because I can't plug it back into the formula for the Fourier transform, or the inverse Fourier transform. Likewise with sine and cosine, they're not good because the Fourier transform of the sine and cosine isn't defined, or the Fourier transform of the constant function 1 isn't defined. All right? So this already rules out the exact signals that I want to deal with. Doesn't seem like the best class to me, but in fact it is. It's going to be a restricted class, but it's going to serve as a foundation for a broader definition. That's the first property. So the function, if the function is in this class S, then so is its Fourier transform. The Fourier transform exists, and so is the Fourier transform. The second property is that Fourier inversion works. Two. All right, Fourier inversion as defined by the classical, by the formula. And that only makes sense even to talk about 2 in light of 1, because 1 says if you take the Fourier transform, you wind up back in the class, so you can take the Fourier transform of this function again, or the inverse Fourier transform of this function. All right, because you haven't left the class of functions for which you can define the integral. So that is to say, the inverse Fourier transform of the Fourier transform of f is equal to f, and same way, going the other way, the Fourier transform of the inverse Fourier transform of f is equal to f. That's what we want. All right? This is the best class of, if we can find a class of functions S that satisfies these two properties, then that's the best class of signals that we can hope for the classical theory. All right, for the classical theory, this is the best thing you can hope for. Now, there's one other property that comes up that always comes up in the discussion. And I wanted to state it now. It's not a requirement of the theory, but it comes up as sort of part of the theory and is actually extremely useful for the further developments. There's a further property, so let me just say that. Further property. An identity that I haven't written down yet, so I'm going to write it down now, and we'll make a certain amount of use of it as we go along, is what's sometimes called Parseval's identity for Fourier transforms. We had Parseval's identity, also called Rayleigh's identity for Fourier series, and there's a corresponding one for the Fourier transform, Parseval's identity. It's also sometimes called the Plancherel formula. It's even sometimes called Rayleigh's identity for Fourier transforms. And it says this. It says that the integral from minus infinity to infinity of, if I integrate the square of the Fourier transform, it's the same thing as the integral integrating from minus infinity to infinity, integrating the square of the function. All right, this is not a requirement of the theory, all right? This is not a requirement of the best class of functions to consider, but it tags along with it. It's somehow almost inseparable from it. And I'm going to derive this for you a little later on today. All right, this has physical interpretation in various fields, depending on where it's applied. This sort of identity comes up a lot in distinct but related fields. And it says something like, you know, you can calculate the energy. You think of the integral of the square of the function as the total energy. So you can calculate the energy in the frequency domain, or you can calculate the energy in the time domain. Or sometimes you think of this as they call this the spectral power. The total spectral power can be computed in the spectrum, or can be in frequency, or can be computed in time, and so on. There's various interpretations. There's various terms that go along with this, depending on who you're talking to. Okay, but mathematically, it's always known as either Parseval's identity or Rayleigh's identity, something like that. And it's analogous to what we had for Fourier series, right? For Fourier series, we had the sum of the squares of the Fourier coefficients. That's what we get on the left-hand side. That's the spectral information. And on the right-hand side, we had the integral of the square of the function, but we only had it over one period. Here, it's integrated from minus infinity to infinity, because the signals are supposed to live on minus infinity to infinity. So I'll come back to that a little later on. And as I say, that's not a requirement of defining the best class of signals, but it always comes up. It always comes up. All right, now, so here's the question. It's not such a stretch to say this is what we want. All right, these are the functions that we want. These are the two properties that we really want our best functions to have. The question is, well, what is such a class? And is there a simple enough way of describing it that's going to be useful, that I can actually work with? And how do you find it? So how do you find such a class? And again, imagine the difficulties. Imagine you are a scientist or a mathematician or an engineer confronting this problem, and as I say, the field is highly developed. Nature has provided you with so many examples, so many different kinds of signals, and so on. How do you choose? What properties of the Fourier transform, what properties of the signals do you choose upon which to base your theory? It's hard. All right, that's a hard intellectual challenge. All right, and it was met by Laurent Schwartz, who was a very famous French mathematician who taught for many years at the École Polytechnique in Paris. So how to choose, how to define S, how to define S. That's the question. How do you isolate a small set of phenomena among all possible phenomena that nature has provided in order to build a reasonable theory? So this is solved by an absolutely brilliant and inspired work. Genius does what genius does. Who can account for it? All right. This is solved by Laurent Schwartz back in the 40s. All right. And I think it's significant, actually, that Schwartz taught at the École Polytechnique. The École Polytechnique is the famous technical school of engineering in France. All right. It was founded in the Napoleonic era to train technically competent Frenchmen, probably not so many French women at the time, to become engineers. All right. And Laurent Schwartz taught there, and Laurent Schwartz was, although a mathematician by training and although a mathematician by published work, was thoroughly grounded and thoroughly familiar with the applications. And as a matter of fact, in his book, his monumental book, it's always referred to, on the subject, which is called The Theory of Distributions, these generalized functions that we're going to talk about are often called distributions, not to be confused with probability distributions. Anyway, in his book on this, I think in the preface, the first sentence of the preface or something like that, he credits not mathematicians, not even scientists, but he credits Heaviside, actually, Oliver Heaviside, with really laying the basis for the whole theory. And what he's thinking of there is delta functions, and what we now call delta functions and things like that, sort of operational, what then was called sort of operational calculus. So it was in a very applied context that Schwartz was thoroughly familiar with, that he extracted, from which he extracted his theory of what's now sort of the more modern foundation of the Fourier transform. It's absolutely brilliant and inspired. And it's very complicated, all right? If you go through all the details, it's very complicated. We're not going to do that. But if you allow yourself to sort of go along for the ride, it's actually not so complicated, and it's a pleasure to see it work, and it's something that you can compute with. I keep coming back to that because I want you to believe me, and I want you to realize that I'm not just doing this for the hell of it. That is, we can actually compute in a very convincing way the Fourier transforms that you really want. Sines and cosines, the delta function, constant function, all that stuff. It really comes out of the theory in a beautiful way. But you do have to accept a certain amount going into it. All right? You have to accept a certain change of point of view and change in perspective. Okay, now, I'm going to give you the property right now because it really is fairly simple to state. And I'll tell you sort of where it comes from and why it comes from, but I'm not going to go through the details even at that, although more details is provided in the notes. All right, so here's the definition. S actually, so S is now not just standing for signals but standing for Schwartz, is the best class of functions for Fourier analysis is the so-called class of rapidly decreasing functions. S is the class of rapidly decreasing functions. And it's defined by two properties. Two relatively straightforward properties. First of all, any function in the class is infinitely differentiable. You don't have to worry about smoothness. It has arbitrarily high smoothness. You want to take 1,000 derivatives? Fine. You want to take 1,000,000 derivatives? Fine. You want to take just 1 or 2 derivatives? Fine. Everything is just fine. So f of x is infinitely differentiable. That's one property. 1. All right, that doesn't talk about the rapid decrease. The second definition is the rapid decrease. And what it says is that for any m and n greater than or equal to 0 integers, let me write down the definition, and let me write it down and then tell you what it means. Absolute value of x to the n, the mth derivative of f of x tends to 0 as x tends to plus or minus infinity. I don't know whether I switched the rules of n and m here when I'm writing on the board with the way I wrote it in the notes, but it doesn't matter. What this says in words is not hard. In words, this says that any derivative of f tends to 0 faster than any power of x. Independently. All right? M and n are independent here. The third derivative tends to 0 faster than x to the 100. Also faster than x. Also faster than x to the 1,000,000. The 50th derivative of f tends to 0 faster than x to the 5,000,000ths. Or whatever. M and n are independent. It says, once again, in words, and that's the way to think of it, is that any derivative of f tends to 0 faster of f of x tends to 0 faster than any power of x. And independently, all right? The order of the derivative is independent of the power. Okay. Now, where this comes from, I'll explain in just a second. First question you might ask is, are there any such functions? I mean, is it terribly restrictive? Already, this certainly does rule out sines and cosines and constant functions. Sorry. Tends to 0 faster than any power of x. This already seems to rule out the functions we'd want, or a lot of functions we'd want. So it's highly restricted. It's easy to write down, but it seems like highly restrictive. And again, you know, why it's a little bit surprising that one could build such a powerful theory, such a very general theory, on such a restricted class. But you can, and that's the story that's yet to be told. Okay? Now, so are there any such functions? Well, I'm happy to write down at least one of them. A Gaussian is such a function. All right? Any Gaussian, I'll take the Gaussian that we've worked with so many times, although it doesn't matter how it's normalized. Any such Gaussian will work, actually. All right? Is such a function. As it turns out that, of course, the function tends to 0 as x tends to plus or minus infinity. But in fact, the exponential is going down so fast that any derivative of the exponential is also going to tend to 0 faster than any power of x. And you know what happens here. If I start taking derivatives of e to the minus x squared, I'm going to get powers of x out front. But I'm also, they're going to be multiplied by this e to the minus pi x squared, which is going to kill them off. And in fact, any derivative, any power of x times any derivative of this function will tend to 0. Check this out. I mean, you know, do some calculation, do some experiments, do some graphs. All right, work it out. Just try it. I'm not going to prove that for you, but it's true. All right, so that's at least it's not a vacuous class. At least there are functions in the class. That's good news. All right. Another important class of functions, as it turns out, are the smooth functions which vanish identically as you get close to infinity. Not just tend to 0, but actually which are equal to 0 beyond a certain finite interval. So C, another class of functions, these are the functions, infinitely differentiable functions, which are equal to 0, identically 0, outside some finite interval. Different intervals for different functions. I'm not saying all the functions vanish outside of minus 1 to 1 or minus 10 to 10 or whatever, but a function is in this class if it is infinitely differentiable and it goes, as they say in the biz, smoothly down to 0. So the graph is something like this. You can do whatever it does, but it does smoothly and it tends to 0 smoothly. So it's identically 0 beyond some certain point, from A to B. And again, different intervals for different functions. I use the word C because the mathematical term for this is functions of compact support. The support of a function is the place where the function is non-zero, and that's a bounded closed interval, and that's called, in the mathematical biz, that's called a compact set or compact interval. And so these functions are called compact support. You will see that terminology certainly in the mathematics literature, and you'll also see it in the engineering literature. It's pretty widely adopted. All right, so that's what the C stands for, compact support. All right, and there are plenty of functions like this too. All right, it's not hard to come up with functions like that. All right, so there at least the function of the class S is populated. There are functions which are rapidly decreasing. Okay, so it's not a vacuous theory. Now, where does it come from? Where does it come from? Why this? Why these properties among all possible phenomena that nature has given you? All right, Fourier analysis is a highly developed subject. There's so many things to choose from. Why this? Why? How did this work? Well, like I say, genius does. Who can account for it? No, but I can tell you what it's based on. It's based on the relationship between smoothness and rate of decrease. It's based on the derivative formulas. That turned out to be sort of the fundamental property of Fourier transforms upon which this theory could be erected and the other things could be understood. All right? So the connection here comes through the derivative theorem. There are various versions of the derivative theorem, but the one that we looked at before was the Fourier transform of the nth derivative. Or I used m before, so let me use m here. Was at s is 2 pi I s to the m times the Fourier transform of f at s. All right? And there's actually a similar formula for the Fourier transform of the derivative of the Fourier transform and so on. I won't write that down. Again, these are in the notes. Now, I said this we used this actually when we talked about the heat equation. And we used it when I said this was actually a fundamental property of Fourier transforms. It turns differentiation into multiplication. All right? The derivative formula at a high enough elevation, if you're looking at it, relates smoothness, that is to say the degree of differentiability, to multiplication, to powers of s. All right? So saying something like this quantity tending to 0, meaning a power of s times, in this case, the Fourier transform tending to 0, says something about how differentiable the function is. It's a relationship between differentiability and measurement in terms of powers of s of rates of decrease. And I'm not really going to say anything more about it than that. All right? You know, that plus about a 250 IQ will lead you to develop a fantastic theory. All right? But anything short of 250 IQ probably will leave you short. Okay? But this turned out to be, you know, it was the derivative theorem and exploiting the relationship between differentiability, between the degree of smoothness and the sort of rate of decay turned out to be the crucial thing upon which this thing hinged, upon which the theory hinged. So it was sort of the connection from differential equations. And actually, again, that comes a lot out of the applications. We didn't do a lot of this, but in Heaviside's work, for example, where he introduced the so-called operational calculus, delta functions and things like that, it was often in the context of differential equations, of solving differential equations. And he would work on solutions of differential equations by taking transforms. All right? And differentiation turns into multiplication under many of these transforms. You've seen probably when you were a kid, the Laplace transform has the same sort of property. Other sorts of transforms have a similar kind of property. All right? So it was one of the phenomena that was out there. But why this phenomena and not other phenomena? I say that's what it took a genius to see. All right, now I'm going to do one more thing today, and then I'm going to show you next time how we're going to use this. All right, and then how we're going to proceed from this very restricted class of very smooth functions with very good properties to functions which are very wild and things that are not functions at all, like deltas and things like that, and how we're going to use this to actually define Fourier transforms for objects which are extremely general. But let me take this opportunity to finish up today with a derivation of Parseval's identity. All right, so this is just, it's off the direct trajectory that we're talking about now, but it comes up often enough, and it's somehow always allied to the theory that I think it's worthwhile actually just going through the derivation. So Parseval's identity for functions in class S now, for functions for which there is no issue of convergence, anything. So Parsifal's identity says, again, the integral from minus infinity to infinity f of s squared ds is equal to the integral from minus infinity to infinity of f of t squared dt. And by the way, for functions in the class S, there is no question about convergence of these integrals because the functions are dying off so fast that the integral of f squared converges. And furthermore, because the function in the function has the class S has the property that if you take the Fourier transform, you stay within the class. This integral also exists. All right, this integral also exists. That is, I should have said that actually. But part of this point here is that not only does the fact that this satisfies the properties that we're interested in is the functions satisfy the property of rapidly decreasing. Also, their Fourier transforms do also, and that's where this relationship also comes in. Okay, sorry, I should have been a little bit more explicit about that, but we'll come back to it. All right, I'm actually going to prove a slightly more general version of this, and it'll take me but a moment. Actually quite a straightforward derivation. The advantage is that everything is justified. All the manipulation I'm going to do of integrals is completely justified. So let me prove a slightly more general one, namely the integral from minus infinity to infinity of the Fourier transform of S times the Fourier transform of G bar ds, an inner product of the Fourier transforms, is the same as the inner product of the functions. Integral from minus infinity to infinity f of t times g of t bar dt. So I allow for complex valued functions here. And of course the Fourier transform generally is complex valued. Okay? All right, so how does this follow? Well, it follows from, let me use x here instead of t. Not that it matters. Not that it matters at all. All right, I'm going to invoke Fourier inversion. That is, to prove this, I'm going to write g of x as the inverse Fourier transform of the Fourier transform. That I'm going to write g of x as the integral from minus infinity to infinity of e to the plus 2 pi I sx, the Fourier transform of g at s ds. I can do that because I can. In this case, I can. If I assume that f and g are in class S, Fourier inversion works, everything is fine. Okay. Then, what about the integral from minus infinity to infinity of f of t, g of f of x, g of x bar dx? Well, g of x bar, sorry, let me do it over here. G of x bar is the integral from minus infinity to infinity. I take the complex conjugate to the inside. So that'll be e to the minus 2 pi I sx, the complex conjugate of the Fourier transform s ds. Okay. So I take f of x times g of x bar, integral from minus infinity to infinity, that's integral from minus infinity to infinity, f of x times the integral from minus infinity to infinity, e to the minus 2 pi I sx, f g of x bar dx, and then the result is integrated with respect to ds, sorry. Then the result is integrated with respect to x. All right. Now, integrate with respect to x. Now, let the rigor police through the door. I don't give a damn. Because everything here converges in every possible good sense. I can interchange limits of integration. I can whip them suckers around with absolutely no fear of retribution. That is to say, brothers and sisters, that this is equal to the integral from minus infinity to infinity, integral from minus infinity to infinity. Let's put them all together and then take them all apart. E to the minus 2 pi I sx, f of x, g of x, f of g of s, bar ds dx. And now that's putting all the integrals together. Now I take the integrals apart and turn that into an iterated single integrals again. And I can do that because everything converges in every possible good sense. You don't scare me. You rigor police you, minus infinity to infinity of f of g of s bar, integral from minus infinity to infinity, e to the minus 2 pi I sx, f of x dx, then result integrated with respect to s. I swap the limits of the order of integration. And you see what's inside that integral is nothing but the Fourier transform of f. So this is equal to the integral from minus infinity to infinity, the Fourier transform of g of s bar the Fourier transform of f of s ds, and I am done. Where do we start? Where do we finish? We started with the integral of the integral of the Fourier transform of f times the Fourier transform of g. No, I didn't. Here's where I started. I started with, where did I start? There I started. Okay, up there I started with the integral of f times g bar, and then they ended with the integral of the Fourier transform of f times the Fourier transform of g bar, and that is what I wanted to get. Ain't life good? All right, and it all works and it's all perfectly justified because the class S is the perfect class for all Fourier analysis. And next time you're going to see how we get from this, what seems to be a highly restricted class, to all the functions that society needs to operate. All that and more coming up.